thank you for joining us. I'm Christian Durier. I'm the CEO of Compliance Robotics, and also I'm a research director at INRIA. I'm very pleased to welcome you in our first live webinar. So it will be the occasion to present you Compliance Robotics and also our robot, new robot, Emio, that is a robot done for education. So Compliance Robotics, the motto of Compliance Robotics is towards agile robotics adapted to a fragile world. So what we mean by a fragile world is the fact that today the robots have done many progress. They have new sensors, new computer, new features, but there is something that didn't change so much, is the design of the robots. And this design is not adapted to fragile people, proximity of fragile people. It's not adapted to proximity to manipulation of fragile objects. And their design is not also adapted to a fragile world, meaning that in particular, they are not adapted to recycling or use of material that are that can be easily found in the planet. So these last years, there has been the growing of a new community of people around soft robotics, which is a new way of designing robots. These robots are adapted to fragile objects. They are less dangerous, they are more flexible, and they are resource efficient. So basically, the idea is to really go to a more efficient robotics that is intrinsically safe, flexible, and energy efficient. So the company is divided into three objectives. The first objective is to provide a new robot for industry. The second objective is to provide robots for education. And the third objective is to provide new simulation approach, in particular for deformable robotics. So in industry, we are developing a new flexible arm that we call hollow, because the robot is hollow. This robot is flexible, is lightweight, and it's capable of performing various tasks automatically. We have also, completely on the right, the part dedicated to simulation. So you can contact us for customized simulation. In particular, if you want to simulate a new robot that deforms, or if you want to simulate a robot in interaction with a deformable environment, we have a physics-based approach to that. And we have experts here in the company that can assist you in designing and controlling your robot. And in the middle, we have the lab, which is the topic of today, because we do a focus on Emio, where we provide new labs, a new approach for teaching basically soft robotics. So let's focus on that, Emio for education. So we have this robot that you see where, in fact, we have different use of the platform. Basically, you have a robot and a simulation. So basically, you can, for free, go to our website and download the simulator, because the simulator is completely free. And with this simulator, you can already do two labs, a lab on kinematics and the lab on design. But of course, the better is to use at the same time the robot and the simulation, where then you can use all the labs. You have basically the lab on modeling, closed loop, pick and place. We'll see that just after. But there is also a possibility of having the robot only. And we have developed a free API where you can, if you are developing yourself your own software, you can plug your software to our platform. It's also possible with this API. So I will now give the floor to Eulalie Kowood, who will present you how to download the software and to install it.
Hi, everyone. So my name is Lali Koubout. I'm in charge of the software development at Compliance Robotics. So 2 days ago, you received an email with links to download the Emio Labs application. I hope you had the chance to test it. If not, that's okay. We'll have a quick glance at it together now. So in the email, you can find the links to download the application for Linux, Windows, and macOS. You have several options for the format, so either portable, an installer, or a zip archive. You also have the requirements, if any, for each system. For detailed instructions on how to install and launch the application, you can refer to the documentation. The link is also in the email. You will find a lot of other useful information in this documentation, so don't hesitate to check it out. So here I have downloaded the portable version for Linux. Once the download is complete, I will just extract the archive and double-click on the executable file to launch the application. When you launch the application for the first time, you will be greeted with an introduction page. So at the top of this page, you will find the default content, which focuses on teaching soft robotics. The application is highly customizable, so you are allowed to modify the existing content or add your own. So if you go to the end of this page, in the Let's Try Emio section, you can click on the SOFA button to launch the simulation software. Even if you don't have the robot, you can still play with the digital twin of Emio. You can start the simulation by clicking on the play button at the top middle of the window. On the right side, you have sliders to control the 4 motors of Emio and also sliders to directly control the effector position. The simulation runs in real time, so you can see how Emio reacts to your commands. You can also program Emio's movement using the bottom panel of the software. This panel allows you to add waypoints, specify the duration of each movement, and create loops to repeat either the entire program or specific sequences. Here, for example, is a simple program I created. So we are continuously enhancing the software and introducing new functionalities, so make sure to stay updated by subscribing to our newsletter. So that's it for me. I hope you will all have time to test Emio Labs yourself. If you have any questions or feedback, please don't hesitate to reach out to us.
Thank you, Lali. And now is Manuela, who will present you Emio.
Hi everyone, my name is Manuela Uti. I am project manager at Compliance Robotics, mostly in charge of Emio. Now we're going to discover the Emio robot, which is a reconfigurable parallel continuum robot that can be used in a compact or an extended mode. In its compact mode, the robot has an upwards orientation and can be used as a joystick by tracking the end effector position. In the extended mode, it has a downwards orientation to form a delta-like configuration and also works either by tracking the end effector position or by opening and closing a soft gripper, which we are going to see later. Both the compact and extended modes are equipped with a 3D camera to allow for computer vision in the proposed labs. Emio is modular, which means that the legs can be changed and the end effectors can also be changed. At the bottom of the slide, you have different effectors, and an interesting one is the soft gripper, which we are going to see in one of the labs later. The platform comes with a virtual twin environment called SOFA Robotics, which has a graphic user interface designed for robotics and relies on physics-based models that are computed in real time, and which you saw at the start of the presentation, that can be downloaded and tested even without the robot on some public labs. So the platform comes with ready-to-use labs and projects that allow you to discover soft robotics concepts such as modeling, simulation, design, and control. And we are going to see these labs now. The first one is the modeling, where the users have to understand the mechanics models of one of the legs before constructing the robot. And the idea is to find the parameters such that the simulations perfectly mirror the real device behavior, as you see in the image. The next lab is kinematics, which builds on the quasi-static resolution of the robot's configuration. And we vary the legs positions and mechanical coupling by changing the N effector, as you see in the images that slide. And this lab also allows you to explore instabilities, like for example, in this configuration with the same position of the legs, you have two possibilities, and you would agree with me that this one is infeasible because the legs will have to cross Emio stop bars. The first learning in this lab consists in actuating the robot and calculating the resulting displacement of the effector. This is called direct kinematics. As you can see in this video, by sliding the motors, we calculate the end effector position in simulation, and it corresponds to the movements of the real device. The next learning consists of having a desired position to achieve for the end effector and finding what actuation should be applied to achieve the desired position. As you can see in this video, we have a program trajectory, which was done as Eulalie showed just before, and the actuation is calculated and applied in simulation and on the real robot in real time. An interesting fact about this is that when you have the models of the different legs, you can change them and change the configuration without any further calculation to achieve the same trajectory. Another interesting fact about this one is that with the soft gripper effector, we do not only control the gripper's position, but we also control its opening and closing by actuating the corresponding legs. And this leads to a pick-and-place project, which consists of controlling the soft gripper and moving it to a given position and opening the legs to either pick or place an object. The next lab is the design lab, in which the users design their own legs. And here we pose a problem of increasing the gripper's workspace, as you can see in the small image. And we provide Python code to design the lab in a free CAD framework. And we also provide solution for the teachers where we increase the legs length and the bending radius. An interesting thing about this is that those who are equipped with 3D printers can print the legs and test them on the real robot. Finally, we have the closed loop lab, which is based on the quasi-static resolution of the robot's configuration and helps the users understand the use of a controller, how the parameters affect the precision. An interesting thing about this is that by closing the loop, the robot's apparent stiffness is increased as the robot is actuated to keep the effector in a desired position. And now we are going to have a focus on this lab with Alex.
Thank you. So I'm Alexandre Krzeski from Compliance Robotics. I'm also full professor at Central Lille, and I will show you a live demo of the closed loop lab. So the first step of this closed loop lab will be to understand why we need to close the loop. And the main reason here is that the open loop situation is not completely accurate. We can model it as the equation we can see here is that the final position of the actuator will be the desired position plus some inaccuracies. I will start the lab right now. So here we can see the sofa simulation, and I will connect it to the robot. And we can see on the bottom graph the actual error between the model, what we predict to have as an end effector position, and the real position sensed by the tracker. Here we have around 2 centimeters of error. The first step of improvement of this will be to create a proportional loop controller. Here we provide all the equation and all the theoretical material to understand what is going on. Then the student will have to code this controller. Here it's just these 2 lines to design. And then we can test for different values of the controller, and we can see that the accuracy is improving as I increase the gain, as the theory will tell. If we change the value, of course, we can see the behavior of the system. And as we increase this value of KP, we will come closer to the stability limit. And if we reach the stability limit is around 2, we can show to the student that the bad controller is worse than having no controller. The next step of this lab will be to switch to a more advanced controller, which is the integral controller, to show the disturbance rejection properties of this one. So I will restart it for you. So right now I'm going too fast. I'm again in the open loop situation. We assume that the student have found the solution, which consists of these few lines. It's an integral controller with anti-wind up system around it. And as I will increase the control gain, we will see that the robot will converge faster to, the error will converge faster to 0. And if we create disturbances, we can see that the motors are pushing more and more to try to reject the disturbance.
Okay, so as we promised in our communications, we have new labs that are planned for next year and which we are going to see now. The first lab is the force sensing lab, in which we transform Emio into a force sensor by observing its deformations and estimating the force that is being applied to the effector. Next, we have this complete project that we propose for master students and which can account for an academic year project. The students should start from scratch by modeling the legs and controlling the soft gripper position. And then we have some computer vision to recognize the pieces, either different colors of the pieces, or like in this one, we increase the level of complexity by placing cats and dogs images on the pieces, and the students design their own neural network to recognize the cats and dogs and play against an operator. Next, we have this dynamics model-based control, which is a sort of amelioration of the lab which we just saw with Alex, where we are no longer in a calisthenic configuration, but we observe the robot's vibrations and add them into the control loop. This next lab is cable actuation, and it's a good example of the program which we want to present today, because it's a lab which we are developing with one of our ambassadors, Professor Jessica Bergner-Skars from University of Toronto. The idea is to change Emio from a parallel robot to a cable-actuated continuum robot. Now, I'd like to discuss our early adopters program, which is open until October 31st. Like we said at the start of the presentation, we have a free plan where you can download our software simulation, access some public labs, and design your own robot legs and test them in simulation. But if you join our program as an explorer, you have premium customer support, you have access to at least one Emio robot, and you have anticipated access to the new labs like the ones we just saw, and your feedback also counts. And if you join us as an ambassador, you have the advantages of the explorers, but you also have the opportunity to create a lab with us, just like we saw for Professor Jessica, and whose testimony we'll have later. On a regular basis, we sell the Emio robot and accessories and additional modules for the new labs. We sell trainings and workshop animations, and we also sell simulation personalizations. For our ambassadors, we have digressive prices. For our explorers, we have digressive prices for multiple Emio robot purchase, and you have a 50% reduction for the additional modules when we have new labs. And your feedbacks are integrated into Emio's improvements. And like I said, you have premium access to the Emio labs. And for the ambassadors, you have all the benefits of explorers, and we give you some free time to work on lab creation and simulation personalizations. We would like to use this opportunity to announce the first edition of the Emio Lab contest, which consists in creating soft robotics open lab using the Emio for Education platform. We have 3 amazing prizes to win, and you can start contributing from November 1st this year until May 28th next year. Now we are going to have a testimony from Professor Jessica Bergner-Kars at Toronto University, who integrated Emio into her teaching lessons.
Okay, hi Jessica.
Hi, Christian.
So today we consider that people who buy our robot are today early adopter, but Jessica was our first customer, so we are very happy and proud to have you as a very, very, very early adopter. So as you bought the robot last year, and so we deliver it at Christmas time period.
Very nice gift. Thank you again.
So thank you very much, Jessica, for your trust. And we just have a few questions for you. Could you briefly introduce the course in which you use Emio?
I used Emio in the Introduction to Continuum Robotics course that I'm teaching here at the University of Toronto. It's an 11-week course, 2-hour lecture and 2-hour practicals each week. And it's a mix of, I guess, traditional lectures and also paper discussions. So it's more an experiential learning course. And in the practicals, we used Emio to give the students an opportunity to work on an actual robot, because in previous offerings, we were mostly working in simulation.
Okay, great. So what are the level of the students?
Undergraduate students, it's offered in 4th year computer science, but also open to graduate students, so master students or PhD students in their 1st year of study. So in the cohort we were introducing Emio, we had 20 students in total, and I think only 2 of them were actually graduate students, so master students. All the others were undergraduate students in their 4th year.
And so what are your main objectives, learning objectives, when you introduce Emio in the class?
Yeah, that was actually great, because Emio kind of addresses most of the course learning objectives that I can tell you about. So one of the learning objectives is that students are able to identify continuum robots and differentiate them from, I guess, conventional robots and from hyper-redundant robots. Another learning objective is to understand continuum robot capabilities and their degrees of freedom. So that's an interesting discussion we had with Emio. Also, they should be able to describe a continuous shape of a continuum robot using curves and differential geometry. So that obviously ties in very nicely with Emio and the whole simulation behind it. They also have to derive and implement kinematics and kinetostatic models, where Emio is also supporting that really well. We also discuss motion planning and motion planning challenges in contact-rich environments, where the pick-and-place task directly ties into, and then they also need to understand and implement open loop and closed loop control strategies, ties in perfectly with the lab, and then explain modeling and control challenges, which we could also explore with Emio. And so that was great to see that all the learning objectives that I had anyway, Emio is directly connecting to all of them.
So you basically tested quasi all the different labs we proposed, or you did select some of them? Yeah.
Yeah, we had to make a selection. I guess as early adopters, that was clear. You had a nice set of labs in the beginning, but we ended up only using the pick and place task programming, because that was easily accessible for our students. And then we adapted the control lab a little bit so that they could compare open and closed loop performance, did some PI gain tuning, and we also ended up using the custom designing of the legs and see how that changes the behavior of the robot. That was also something we ended up using, but we had to make some adaptations.
And was it easy to integrate Emio in your teaching activities?
In general, I would say yes, because I think the software design is really easy to make changes. I love that it was all the markdown files that you could easily customize. That was very accessible to us as computer scientists. The simulator is fast and it's really accurate and really nice to see. That is very important. What I really liked is that the whole pre-programming of tasks is somewhat similar to what the students are used to from their introduction to robotics course, where they use Franka and Mika Panda robots. And so this whole, like, I guess, task drag and drop, that was something that the students knew. So it was very easy for them to pick it up quickly for the pick and place task, for example. That was really easy, but I guess, well, there's always challenges as your first adopter. I think most of the labs that existed when you shipped the first version of Emio were designed with engineering graduate students in mind. And so I faced quite some challenges because the biggest portion of my course was computer science undergrads. So their background was, I guess, not the same. So they had never heard about finite element modeling that goes way above their head. They don't know quadratic programming, which I found out from my colleagues that that's something I couldn't build on. And obviously in computer science, we don't teach design. So CAD to them was also unfamiliar. So we had to make certain adaptations and couldn't use the, I guess, advanced models that you have in the labs because it was just going way above their head. But if I had to use it in a graduate course, I think I could have readily used your labs. But we had to make quite some tweaks. But it didn't end up being a problem because we, as it said, we taught the course in simulation before. And so we used our simulation of tendon-driven continuum robots, piecewise constant curvature models from before. And then Emio was just used for some labs. And that was a great thing for the students because they could do coding, which is very natural to them, but then also experience the real robot with some tasks. And so it ended up being a perfect course and the students loved it.
Good, great. And which concept in continuum robotics did Emio help to illustrate?
In this particular course, I think the controller tuning was the ones that the students loved the most.
Okay.
The pick and place was also pretty cool, but I think it was quite limited in what the students were able to do then. And so that was, I think, well, students those days they were bored, I think, pretty easily, whereas I was so excited about it. But yeah, mostly the controller tuning. I wish it was the modeling, but I think students are just struggling with modeling in general. And so that wasn't necessarily.
Yeah, I think control, you can really interact with the robot and see the effect of the controller.
Yeah, and also with like any imperfections in the camera. So they for a lot of students, it was just like, oh, there's all these dependencies. And if there's some calibration error, that to them was just really, really, you could see it click in their minds.
So Jessica, you accepted to be part of the ambassador now program. So you will work on the evolution of Emio. Can you just talk a little bit about it?
Mm-hmm. Yeah, I plan on continuing to use Emio in my teaching. And as my lab is very much focused on tendon-driven continuum robots, I would like to see a tendon-driven continuum robot on the Emio platform. And there's some ideas we're already discussing, so I think that will be super exciting. And then probably develop a few labs that are more introductory level, so for this undergraduate student cohort, so that we can maybe have a little bit of an evolution of more advanced labs for graduate students and simpler entry-level labs for computer science students.
Okay, great. So thank you very much, Jessica, for this testimony, and I'm really happy to have you in our new ambassador program.
Same here. I love Emio and I'm happy to support compliance robotics in any way I can.
So thanks, Jessica, again. So the early adopter program that we just presented today is active until the end of October. We already have some support from different university and engineering school. So we already have now more than 150 master students that have been trained on Emio. So don't hesitate to join us. Yeah, can go. And we are happy to answer your questions. So we have like 10 minutes remaining. If you have any question, any remark, it could be just a remark if you have no question. But we are now open to answer your questions. There is already a question in the chat. So it said that. So Adi is saying, hi Christian, Jessica, fantastic initiative. May I know your suggestion for teaching resources like textbook that can support Emio's integration in a soft robotic module? It's a good question, Adi. I've been actually writing a book chapter, and we have also some previous work that have been done. So we can provide a textbook if you think if you want with Emio, and we have also some slides that are available. So if you want to have to have the base of the slides to support the class, it's also available. Yeah, Olivier, maybe. Let's see you.
Yes. Okay. Raising hand doesn't work on the system, but thanks you for letting me speaking. I am associate professor in Brest in INIB, and when I saw the Emio robot in the GNRR in Rennes 2 weeks ago, I decided to buy one because we are just on the verge of teaching compliant robotics in my mechatronic department. So I did launch the order, so I should receive one soon. But I have no skills on compliant robotic, but we have engineers and researchers in continuous mechanics here in Brest. So we want to use their skills on mine in robotics to make something nice. And from your presentation of the Emio robot, it seems that it is the good tool for me now because it looks simple, efficient, and with a lot of resources around it. So I appreciate this because what we are missing most here when we are teaching and researching, it is time. So the time to develop the labs, it's too much usually. So here it's possible maybe to do it with you. I have a few questions. First, I did not understand if the inverse kinematics is included in the simulation or it is also included in the control.
So the inverse simulation is based on the model that is simulated. So you can use it in the simulation even without buying the robot. If you download the software, you can already test the inverse kinematics. But of course, when you have the robot, the real robot, and you want to control it, you can use the inverse kinematics, of course.
So we have all the code coming with the robots with the inverse kinematics?
Yeah.
Okay, good. And also, I know this system is non-linear, okay, because it's a continuum robot. But your control seems to be with PIDs. So it's a linear controller. So how do you match the non-linearities of the system with the linearity of the controller? It's just because you are very efficient with the PID controller?
No, there are two cases. On the cases of the demo, we are using the inverse kinematic to linearize the robot. So the model becomes a simple pure delay, and we just need to close the loop around the pure delay with some disturbances. On the lab, we will propose next year about the control based on the dynamic model. Here we have to linearize, so it will work around the equilibrium point. So this is for master level students. But we can go beyond and we can propose nonlinear control based on LPV modeling that can allow to model the robot all around the full circle and to control it.
Okay, so it's incoming, a lab with non-linear control.
Yes.
Okay.
Yes.
And also, the system is 4 degrees of freedom actuated system. Okay, it's over-actuated if we just control the XYZ position. And you have what do you do with the 4th degrees of freedom? I see in one of your lab you have the gripper. So I guess the degrees of freedom of the gripper is this 4th DOF. But if you are not using the gripper, what can you do? Or did you do something with the 4th degrees of freedom?
Yeah, this is also part of the thing the students discovers with soft robotics, is that there is a lot of degrees of freedom into a deformable structure. So you can have a lot of degrees of freedom that are actuated. But here in the case of the robot, we control. So in the case of the control we show here today, there is no gripper, so we control exactly as you say, 3 degrees of freedom for 4 motors. So in fact, when you compute the inverse kinematics, you do an optimization, and in fact, to do your optimization, you could have an issue with the last degree of freedom. And what we do is that we also minimize the deformation energy to have a unique solution to the problem. So we minimize the solution to the position of the robot, the desired position, plus we minimize also the deformation energy.
Okay.
But this is something that is explained actually in the lab.
Yeah, I'm sorry I didn't get time to go through the labs on your resources. I'm going to do it, but right now I did not. I just have two more questions. You spoke about a contest for master students. Yeah. When will it be?
So basically, the idea is that so now we have already some Emio that are in different places, like in Toronto, in Singapore, etc. So there are most of the people that are using this robot is for master students, and for master students, what they give the robot and for doing a project. So if you plan to do it for instance, you have a group of 2 or 3 students that want to do a project on Emio. Basically, if they agree to do a new lab, a new content, like put Emio in a different configuration, use it for something new, etc. Basically, the students can do their work, then they can send us a video plus the lab. So basically, we provide on our website a new way of designing a lab. It's really easy. It's like markdown things. You can easily write your new lab. And based on the content we will receive all along the year, we will decide at the end of the year. So basically, we close the competition on the 31 of May next year. But you have all the year to provide the content. Again, it's just a video and a lab, and based on that, we will decide the 3 best contributions, and we will reward them with prize.
Okay. Okay. I'm not sure because
to motivate students with basically a new competition. They can also participate. I want to say that so they can participate based also on the software part. I mean, on the free part, it's also possible. They can contribute to the free.
Okay, thank you. It's Christian. That's it.
Yeah.
Okay, and my last question. I'm sorry I take time, but I wasn't. I first ordered the robot, but then I was interested in your cooperation programs, and the one I was looking for is the early adopters, because it is what I am.
Yeah, so basically in the early adopter, there is 2 differences. There is the Explorer, where basically the idea is that you will be a user of the current lab, and basically based on your feedback, we can also improve the current lab. And there is the ambassador. The ambassador is that the idea is that you create new content for like Jessica will work on the continuum robots. We have also a contribution from Maud Marshall on making the Emio as a haptic device. So you have this example of ambassador where basically they create new content completely from scratch based on Emio. And for them, what we reward is that we provide some time. In fact, we really help. We provide the engineering hours to create the new lab, so that the professor doesn't have to create to spend too much time on it. But if you agree to create new content, you can be an ambassador.
Yeah, but right now I didn't have the experience with the robots, so I think it's too early for me. But so the Explorer set will be fine.
Yeah, the Explorer is perfect for you.
And I can join this program even though I didn't order yet the robot?
Yeah, of course.
Okay. So I have until the end of October, that's it.
Yeah, exactly.
Okay, I will try to do this because my last remark is that my ambition is not only about teaching with this robot, but about research also. And we have a postdoc fellow here in Brest that is working on the compliant mechatronic systems. And she's going to build some arms, some grippers with polymers or plastics. Okay. And I think I would like to adapt this her work with your robot. Do you think it's possible to add new stuff, new mechanical parts, flexible parts to your system?
Yeah, of course. Yes.
And new motors also, it's possible.
New motors is a little bit more complex, maybe, but okay. Yeah, maybe. Yeah.
Okay, thanks. I don't want to take all the time. Thanks for your answers. It's very interesting. Congratulations for the work.
Thank you.
Thank you. So Matt.
Yes, thank you. Thank you very much for the presentation. Yeah, very interesting and very interesting to hear about it. Yeah, I'm coming from Berlin, Gentle Systems. We are doing a small R&D project right now on compliant and soft robotics, and I'm just getting into the field. And my question is about Emio and its inverse kinematics model that you're using and that you were talking about. So my question is it using or leveraging the SOFA soft robots inverse module, or is it some kind of completely different model used for that? And if you would adapt a system as you were discussing with Jessica for tendon-driven continuum robots, would you, what approach would you choose for this direction?
Thank you for the question. So basically, right now the robot is using SOFA, as you said, SOFA inverse modeling approach. But as I said at some point at the presentation, you have also an API where you can use your own software. So basically, for the case of continuum robots, for instance, for the tendon-driven, I know that there are other approaches that can do inverse kinematics, like geometrical approach. So it's completely possible to use other model. And right now we are also it has not been mentioned, but we are also creating a new lab based on AI to compute the inverse kinematic. So here so basically we compute the model based on SOFA, but the inverse kinematics is computed with AI, so it's learned basically. So you have different techniques, but of course the one that is implemented and is really easy to use is the one with SOFA, because it's come with the SOFA, the simulator, etc. And basically the idea is to learn how the mechanics can be inverse to drive basically your robot. Is it clear?
Yes, it's clear. Yeah, thanks. Looks like a very interesting platform. Thanks.
Okay, thank you very much. So it's already 2:35. I don't know if there is a last question, maybe. maybe in the chat, is there a way to get your slides in PDF to present it in my teacher colleagues in my school? Yeah, don't hesitate to contact us, and we can send you the content. But there is already a lot of content in the website, so don't hesitate to go into our website. There is already a lot of content about what is inside the different labs. Okay, so thank you very much, everyone, to join us today. We were really happy to have you and to present you Emio. Don't hesitate to book a meeting. It's really easy. You go to our website and you click, and we'll be happy to answer your different questions.